So I'd like to welcome today Marius Celette, CEO of Alpha Impulsion. Marius, thank you for joining me.
Yeah, no issues. A pleasure to meet you, Richard. A pleasure to be here.
Let's start. Alpha Impulsion is a fairly new company, so tell me a little bit about it.
So Alpha Impulsion is actually quite a young company. We are founded in 2022, in late 2022. So we are a bit over 3 years old now. Initially, when we founded the company, the goal was really, crystal clear. We were there to research, develop, industrialize, and commercialize a very specific technology, which is called autophage propulsion. And so at the time we founded the company, we also applied for a patent on the actual technology. And since then, we've come quite far because we actually test fired the technology, this new kind of rocket engine, for the first time last year. And now we're moving to actually, commercializing it and selling actual products to our customers.
Okay. So looking at a bit of background about the company, you were awarded a prize earlier this year for a self-consuming propulsion system. Now,
yeah.
What's exciting about that is it almost eats itself to create the thrust. That's very exciting. How does that work?
Yeah, so obviously, when we founded the company, everybody in the team was quite excited about the technology. But it was obviously great news earlier this year when we heard that the European Commission was also excited about technology and they were willing to fund us. Because it's always something to believe in a project. It's always better when you've got other people who believe in the project as well. To talk a bit more about the technology itself, so it's called autophage propulsion, so literally self-eating propulsion. The basic concept is that we want to use the structure of the vehicle, so it can be any vehicle, like a rocket, a satellite, or anything that's rocket engine powered, basically. And so we take the structure of the vehicle and we use this structure as fuel. So it burns kind of like a candle. So for a rocket, you can imagine at liftoff, you've got a 20 meters high rocket. And so it basically shrinks during the flight as the engine consumes the rocket itself. And at the end of the flight, you're left with only what's useful to get to the final destination, which is the rocket engine and the payload you wanted to send there. When you compare that to conventional rockets, obviously you can see there's huge improvements, because for conventional rockets, you're basically sending empty tanks to orbit. And it's basically just dead weight for the rockets. It's something you have to carry with you, so it's less performance. Then you end up with debris in orbit if you don't manage to deorbit that. It costs more because you have to manufacture those tanks. There's more logistics. There's more risks. So yeah, basically the more parts you can remove in the rocket, the better. That's why we moved on from historical rockets with 4 or 5 stages. And we kind of simplified that down to 2 stages. In our case, it's kind of a continuous staging. So we just really have out of our factory the engine, the payload, the fairing, and everything else is just fuel. So as simple as we can make it to be.
Now, has that got an environmental implication because you're actually using the housing and it doesn't get discarded? That must be good for the environment.
Yeah. So actually, again, not a very complex solution. I know that there's a lot of companies out there working on the chemistry, the combustion, to kind of optimize all of that. In our case, to be honest, our fuel is kind of the same as classical rocket engine fuels like kerosene. So the simplest solution, just use less fuel. So the rocket itself is more efficient. So what we computed actually is that we've got for the same size of rockets, twice the payload capacity. So for the same payload, we've got half of the fuel. So we just pollute half as much just because we just remove some of the fuel. So it's quite a simple solution to the issue, to kind of decarbonate the industry. And it's directly applicable to all kind of applications. I mean, we've been talking about rockets, but same thing for satellites and anything else.
So what about the cost implication? Because you've mentioned it's simple. Yep. Clearly it isn't. It's an amazing innovation. But with the way you've gone about this, there must be a cost implication to people who are going to use this technology.
So it's actually a different implication depending on the application you're looking at. So for rockets, basically we just try to kind of simplify the rocket as much as possible. And so by doing so, we remove a lot of complex systems, especially I was talking about the staging. So removing staging altogether, it really simplifies the rocket architecture quite a lot. Because usually for classical rockets, where we've got different stages, it's like you're building two different vehicles, you're putting one on top of the other. So it's not half the cost, but at least we remove a lot of the manufacturing costs. We also remove a lot of the manufacturing costs due to removing the structure. And then we also have twice the payload. So obviously all of that together, it's just multiplicative. So what we estimate, and obviously you have to take all the numbers with a grain of salt. What we estimate based on a NISA costing framework is that we can reduce the costs of launches by up to divided by 6, which is obviously a huge number because we just completely rethought the way the rocket was going to work. Yeah. For satellites, it's a bit different because for satellites, usually there's no staging for satellites. It's just the same kind of fuel. It also depends on the mission the satellite has to achieve. What we realized is that for most, low Earth orbit satellites, there's no point in having a very fancy propulsion system because they're in low Earth orbit. They have to do some station keeping, have a bit of delta V. It's fine. But for some classes of spacecraft, for example, if you have to do a big transfer, for example, LEO to GEO, terribly expensive. If you have to do interplanetary, terribly expensive as well. Or if you have a space tug which needs to move a lot, in this case, you get really, really big delta V. And in this case, they still don't consider staging, but they have huge losses in terms of mass penalty. In our case, we can reduce the mass of the spacecraft by minus 40%. And so obviously, if you reduce the mass of the spacecraft, you remove a lot of the launch cost as well. And so in this case, the cost advantage is not the system itself, but the launch costs you would have incurred if you didn't use it. So minus 40%. And obviously, it's a huge impact on the margins. For some of the crazier projects, it makes unfeasible, for example, interplanetary projects feasible and commercially viable. And for all the more classical projects, for example, geo satellites, they don't have any issues reaching geo at the moment. But obviously, if they can increase their profit margins, it's very pleasing to the customers.
So taking into account what you've said, there's obviously a defense application here because it's not just satellite. And I know that you're working with the Defense Innovation Agency. How is that tie-up working?
Well, obviously, space has started to be considered by all the defense actors as very important. It's the same thing as what happened with, the air domain a century back. What has happened with cyber, maybe 2 decades back. I'm not an expert on the topic, but basically they've started to, take into account that they are dependent on a lot of stuff, especially from space. In our case, quite humbly, we have actual concrete application we've been discussing with the French MOD, mainly for in-space action related to, having satellites basically move a lot very fast, which is perfectly compatible to what we propose, which is a lot of delta V, so a lot of possibility on the mission size, and still chemical propulsion, which is quite important if you want to be quite reactive. And the other one is reactive launch. So having very, very small rockets to launch payloads, not on a moment's notice. And so that's how we got in touch with the French MOD. And so that's how we got the funding from the Defense Innovation Agency. And so with this contract, basically, we're kind of accelerating the development of our in-space propulsion system, which is called OPAL. And so kind of accelerating the qualification of the system because we want to commercialize it next year. So obviously the timeline needs to be quite compressed. And the other thing is that we have some funding to look at those applications. So that's how the MOD is basically funding us for us to look at those.
Well, Marius, good luck. It's been a pleasure talking to you today. Thank you.
Well, thank you again for the questions and thank you for the invitation. It's been a pleasure as well.